Our next speaker is Simon Foreman, who's an assistant professor at the Department of Physics of Arizona State University. I believe we learned about effective field theory of the large-scale structure together at the summer school in Les Houches 12 years ago.
Right.
He was a PhD student at KIPAC from 2011 to 2016, working with Leonardo Senatore and many others here. He's an expert on perturbation theory for the large-scale structure, the effect of baryons on cosmological inference, as well as all things line intensity mapping. He has done key data analysis for CHIME and is a member of the successor experiment CHORD, as well as PUMA.
Check, check, check. All right, sounds good. Great. Yes, thanks, Manu, for a very comprehensive introduction. And thanks to the organizers for allowing me to speak to you today about the new and exciting field of line intensity mapping. This is a way to make maps of the universe which are a bit fuzzier than the maps that Juno was talking about with spectroscopic surveys, but nevertheless could teach us interesting things about astrophysics, cosmology, and fundamental physics. There we go. So Juno told us to look towards the past. So here's a picture from my past. This is 2016 graduation day at Stanford when I got my PhD. So there I am looking goofy in my graduation robes, and you'll recognize many other people in this figure, some of whom even managed to look goofier than me, which is a pretty nice accomplishment. And so I show this picture not only to take a walk down memory lane, but also to emphasize that a lot of the scientific developments that I'll tell you about have taken place since this time, since 2016. So it's only in the last 5 or 7 years ago that the field of line intensity mapping has really come into its own. And there's been a lot of progress, which I'm excited to tell you about. So to set the stage for what I'm talking about, we can try to summarize the main technique that Juno was talking about in one slide. So in a large spectroscopic survey, you're trying to map out the large-scale structure of the universe by measuring objects one by one. So you'll typically start with some imaging, some high-resolution imaging to identify the sky locations of individual objects, such as galaxies. You measure a spectrum from each one. You look for familiar features in the spectrum and how much they've shifted based on a certain redshift. And then you associate that redshift with a line of sight distance to the galaxy. And in this way, you can build up a 3-dimensional view of the large-scale distribution of matter based on where all of these galaxies are sitting with respect to other galaxies at various distances. This has been a very successful technique for mapping out large-scale structure, as we just heard. And there's a lot to be excited about in the future as well. But there are also reasons to ask whether there are other complementary ways that we could try and map out this large-scale structure. And there are a few different motivating questions that we can think about. One is, what about the dimmer objects? If we're counting objects one by one, we'll only be able to count the objects that are sufficiently bright for a given survey. But there's still interesting information about cosmology and astrophysics in the dimmer objects that we can't actually pick out with a given survey. And so we can ask whether we can harness that information in some way. We can also ask, what about the earlier universe? Perhaps we want to make maps at earlier times when there aren't that many bright galaxies around, or maybe in the so-called cosmic dark ages when there are no galaxies around, but there are still gas and structures that we can use to learn about cosmology. And finally, complementarity is a big thing that we want to go after in cosmology. I think if there's one lesson from the past 5 to 7 years in cosmology is that we can learn a lot by trying to measure the same things different ways. So there are these now infamous tensions in cosmology, the Hubble tension, the sigma 8 tension, which have come from trying to measure the same thing in different ways. And what we found is that these different measurements sometimes disagree. And there's some lessons to be learned there about the data that we're taking, perhaps how the data are analyzed, or perhaps the theory that we're using to interpret the data. And so moving forward, I think we still want to ensure that we have a lot of complementarity in the ways we're learning about the universe with independent measurements with different systematics that we could potentially combine later in larger joint analyses. And so there's a clue to where we might want to go if we're thinking about other ways to map large-scale structure. And that's the fact that a lot of useful information about cosmology is living purely at the large scales. So for many of the big questions we're interested in, we don't necessarily need this very fine-grained map of the structure in the universe. We'd be perfectly happy with some fuzzier map which retains all of the large scale clustering features. If there's an observational way that we can just directly get this fuzzy map, then this might be very useful. Some examples are things like cosmic expansion. We know the BAO standard ruler lives on these very large scales, and we could use this to learn about dark energy. There are also statistical signatures of certain models for the very early universe in theories of inflation that are imprinted in the statistics which are living on large scales. And finally, we can measure the average growth of structures to figure out whether general relativity is truly the correct theory or whether there might be some interesting deviations there. And to think about how to directly make this fuzzy map, we can go back to our basic knowledge of astronomy and some of the observational tools we use, which come from transitions in different atoms and molecules. So we know that there are various ways where atoms and molecules can go from one energy state to another energy state, and then they'll emit photons with known wavelengths. So these include the Lyman alpha transition and various vibrational and rotational transitions in molecules that range from the UV up to the infrared and the microwave, and even longer wavelengths to the radio. And so there's all of these different tools that we can use to try and access different atomic and molecular species which are living in the universe. In particular, if we know there's some gas or there's objects containing some atoms or molecules with an interesting transition, we can imagine just making an observation where we tune our telescope to make just a map of all the radiation in the sky at a given wavelength. And if we understand the ingredients of this map, and if we can remove some contaminants, then we can associate fluctuations in this map with fluctuations in the density of the gas or the objects which are containing these particles, which are undergoing these transitions. We can do this without counting objects one by one. Instead, we're just aggregating all of this radiation and relating it to the objects or the gas that we know are doing this emission. We can, oops, went backwards. We can extend this idea a bit. Sorry, there's a bit of lag here. We can extend this idea into making multiple maps at slightly different wavelengths, with each wavelength slightly longer than the wavelength of the previous map. We know that if there's gas sitting at some distance from us, we're going to measure its emission with a slight redshift and with a slightly longer wavelength. And therefore, if we're making maps of structures at different wavelengths, we can associate each map with structures at a slightly different distance from us. And this fills out the third dimension of the three-dimensional fuzzy map of the universe we want, right? We have the sky direction just in the map, and then the redshift or distance direction in making maps at different wavelengths. And so this composes the technique of line intensity mapping. It's a way, again, to directly get this fuzzy map without having to count objects one by one. And it naturally addresses some of the questions we had earlier. If we're just mapping all of the photons at a given wavelength, these maps are telling us about both the bright and the dim objects that are undergoing this line transition. If we're just making maps of radiation, these maps are also going to contain imprints of the gas outside of galaxies, or the gas which is already around at times when there are no galaxies which have formed yet. And we just saw these transitions often happen at very different wavelengths that we'll use for spectroscopic surveys. And therefore, we need different telescopes, by and large, to make these maps. There are different systematics, and therefore there's a large amount of complementarity because we're trying to map out many of the same structures, but in a very different way. Now, this technique has a long heritage at KIPAC. On the experimental side, there's some nice participation in experiments like the CO mapping array project, which has outfitted existing radio dishes at Owens Valley here in California with new receivers that can make maps of rotational transitions in carbon monoxide. We already heard a sales pitch from Curate about the SPT SLIM project, developing new detector technology that will be mounted on the existing South Pole telescope to make similar maps. And then on the theory side, Tony Lee, whose picture you already saw on the first slide, wrote one of the seminal papers about simulating and modeling what you might see from these kind of experiments. Dongwoo Chung, who's also here at this conference, has done a lot of theory work on delineating the space of models which you could potentially constrain with these kind of observations. And so we'll hear more about these developments from Dongwoo later in the conference. And Emmanuel Shan has written a series of very nice papers about broad modeling frameworks that you can use to interpret these measurements. And so overall, there's been a lot of activity in this area at KIPAC in various directions, and I'm looking forward to seeing that continue. in the future. Now, at this point, it's useful to pivot and talk about a specific example of line intensity mapping, which is near and dear to my heart and has seen a lot of nice progress in recent years. So now we're thinking about the hyperfine splitting of the ground state of the hydrogen atom. In a single atom, if you have the spin of the proton and the electron, which flip from aligned to anti-aligned, we know that this atom will release a photon with wavelength 21 centimeters, or frequency about 1400 megahertz. And on its own, if you have a hydrogen atom sitting in the lab, you'll be waiting a very long time to watch this transition happen. However, there's an extremely large abundance of hydrogen in the universe, and this makes up for the rarity of this transition atom by atom. And it still makes this a signal which we can detect in aggregate by making large maps of the sky at 21 centimeters or longer wavelengths. This wavelength is long enough, in fact, about this large and longer, that it falls into the radio part of the spectrum. And so we need a radio telescope to try and make these maps. Radio telescopes are big. To do this kind of mapping, we generally need some gargantuan single dish like they have at Green Bank or Parkes in Australia, or an array of dishes like they have at GMRT in India, spread over a very large distance. And then you can synthesize the signals from individual dishes into maps that you can then interpret. Now, some of these existing facilities have been used for 21 centimeter mapping. And in fact, some of the first detections were made by the Green Bank telescope and the Parkes telescope. But when people started thinking seriously about this idea in the early 2010s, they realized that these existing facilities aren't necessarily optimized for this telescope. What you really want to get the most power from your 21 centimeter maps is a new telescope, which is custom designed to have the right survey strategy, the right sensitivity and systematics control, and so on. And there was a group of a few research teams in Canada which started thinking about proposals for this kind of telescope. They settled on a proposal that they liked, and then the rest is history. So flash forward a few years, and this proposal now exists on the ground. So this is the Canadian Hydrogen Intensity Mapping Experiment, or CHIME for short. It's located in the Okanagan Valley in British Columbia. So in the west part of Canada, almost directly north of here. CHIME is composed of 4 cylindrical parabolic reflectors, each of which is 20 meters wide by 100 meters long, which are all oriented in the north-south direction. On the focal line of each cylinder are 256 dual polarized radio antennas, giving you 1,024 antennas total in the experiment. The telescope is designed to focus radio waves coming in from the sky onto these antennas sitting on each focal line. There's custom electronics which digitize and channelize these signals and then correlate the signals from every antenna with every other antenna. These correlations are stored, and from there we can use the principles of radio interferometry to reconstruct a map of the radio sky. Importantly, CHIME is designed to have no moving parts. We don't physically tilt it to look in different directions. Instead, we sit there motionless, let the sky drift overhead every night. And then after the fact in software, we can effectively virtually point the telescope in many directions at once and make maps of the sky. We do this to make a map of the entire northern radio sky down to declination around -20 degrees every night. CHIME has been operating at full capacity for 5 years so far, and we save about 1 terabyte of data per day. So not quite LSSD scale, but still what I would call big data. Now, one of the nice features of this design of CHIME is that it looks at so much sky area every night, is that it's become one of the premier instruments in the world for discovering and monitoring radio transients. So that's a whole nother talk, but that's also something which CHIME has been very successful at. The CHIME collaboration acknowledges that the telescope is located on the traditional, ancestral, and unceded territory of the Syilx Okanagan people, and we're grateful for the opportunity to live and perform research on this land. Here is a forecast that demonstrates what kind of cosmological science you could get out of CHIME. This is a somewhat idealized forecast for measurements of cosmic expansion history in terms of dV, this volume average distance measure, normalized to a fiducial prediction for it. So the only thing that's important here is the sizes of the error bars. A forecast for CHIME of after 1 year of clean integration time is shown in orange, and the other colors show similar forecasts for DESI. What this shows is that with this kind of custom-built telescope like CHIME, we can in principle obtain constraints on cosmic expansion and similar cosmological quantities which are competitive with DESI. And so there's a high degree of complementarity, which is in principle possible here with an observational technique, which is extremely different with different systematics. However, you'll notice the important aspect of this label here. This assumes no foregrounds, no systematics for CHIME. With the CHIME data set that we currently have taken already, we have the statistical power to achieve these constraints, but we're only systematics limited. And so within CHIME, all of the effort is going towards mitigating systematics and removing foregrounds and trying to get the robustness of our analysis to the level where we can realize this statistical constraining power. The way things look today, we could summarize like this. Here's an example map of the sky, of some portion of the sky from CHIME data at 700 megahertz, which corresponds to 21 centimeter emission from redshift roughly 1. In this map, you don't see any 21 centimeter. What you mostly see is diffuse synchrotron emission from the Milky Way, which is the diagonal pattern along the plot. And you see various bright radio point sources, each of which show up as a bright central lobe with 2 slightly dimmer east-west lobes. And this is a coad of 102 nights of data, which is about 1/10 of the total volume of data that we have so far. Now, in order to try and get the signal we want, we need to apply some fairly aggressive filtering to this map. Without going into the details of what this filtering is, we can apply various steps to remove roughly a factor of 5,000 in fluctuations in this map, and then get much closer to the signal we want. What you see now in this map is a combination of artifacts from bright radio sources and thermal noise of the instrument. You still don't see any 21 centimeter here. You're mostly just seeing noise. And so we need to apply some summary statistic to try and tease out the signal we want. For our first analysis, the way we've done this is to use a cross correlation. So appealing to our friends in the spectroscopic galaxy survey community, we know that the EBOS survey, part of Sloan 4, has measured the positions and redshifts of many galaxies and quasars. And what we expect is that at each of these positions, there should be some hydrogen associated with these objects. So we expect to see a slight excess of intensity in our maps at each one of these locations. What we can do is consider the angular position or the sky position of each one of these objects and take, take the value in the map located at the same position and at the same redshift, or located at the same position, but at a slightly closer line of sight distance or a slightly farther away distance, and effectively measure a one-dimensional correlation function as a function of line of sight distance away from these objects. What we expect to get is some kind of line of sight profile of the 21 centimeter emission around each one of these catalog objects. And since we need to do some statistics, we average over all of the objects in these catalogs. And these are the results we get after we do this. So the black points are the measurements connected by lines to guide the eye. The red curves are the best fit theory predictions, which also incorporate the filtering we've done, which is why they have this funny sync function-like shape. And the bands denote 1 and 2 sigma error bars, which we get from stacking on random catalogs. So we find significant detections of the cross correlation between the 21 centimeter signal and ELGs, LRGs, and quasars from EBOS with signal to noise roughly 6, 7, and 11, respectively. So we get significant measurements of the cross correlation with all 3 catalogs. And this represents a milestone for 21 centimeter intensity mapping in several respects. It's the first such measurement with a custom-built instrument with an interferometric telescope and at redshifts greater than 1.2. Now, unfortunately, the filtering we had to do to the data, given our current data quality, was so aggressive that the cosmological constraints we end up getting from these measurements are fairly weak. And so I won't go into detail about those, but we're currently working on improving the analysis and coming up with new analyses to try and get more interesting cosmological information. However, there were some interesting things which came out of this measurement which point toward future directions to go in for some scientific targets which weren't originally on our radar, but which we've become aware of after doing this analysis. One thing is if you think of the centroid or the peak of this cross correlation for the quasar stack and you ask where it is, physically you would expect the peak to be located at the redshift of each object. You expect the most 21 centimeter emission coming from the objects themselves. because at these redshifts, H1 is living in galaxies. For the quasar stack, we measure this centroid and we find that it's slightly shifted away from the 0 point. And this shift is significant at about 3 sigma. We actually have enough quasars that we can split the catalog up into several redshift bins and measure this shift in a few different bins at a few sigma each. We interpret this as a systematic bias in the quasar redshifts from the EBOS team that we've used for these analyses. And these redshifts are more or less determined from quasar emission lines. Actually, they're determined from some PCA fitting procedure to a bank of templates. But there's a lot of information about quasar emission lines in these redshifts that are provided by the EBOS team. And it's well known that redshifts derived from quasar emission lines are often systematically blue shifted with respect to the true redshift of the quasar because of physical processes occurring at or near the quasar due to things like outflows. Our measurements of this offset are consistent with what the EBOS team has measured internally based on a limited number of host galaxy identifications of these quasars and measuring those redshifts. But we've measured these shifts completely separately, right? We don't need any quote unquote true quasar redshifts. We've only measured this from the correlation with large scale structure. And so as the size of the quasar catalogs increases and as our data quality get better, there's the potential to slice up the quasar catalog into more redshift bins based on other properties of the quasars and get more independent measurements of systematic shifts in these emission lines, and then maybe learn something about the physics of quasar outflows or something else about quasars from this. And there's a few other things which come out of this analysis, which I won't get into, but they point to some science which just appears and which is impossible to ignore when we try and start with other science targets. And so I find this quite exciting. And I think there's a lot more to explore in these kind of measurements along these lines. So just quickly before I wrap up, there's another recent measurement from CHIME that I'd like to highlight. We can also think about the Lyman alpha forest, which is also measured by the EBOS survey. So remember, the Lyman alpha forest is the name for dips in the spectrum of a quasar when emission from quasar passes through some cloud of neutral hydrogen and it's absorbed by the Lyman alpha transition in this neutral hydrogen. So in a quasar spectrum, we expect to see dips whenever we see neutral hydrogen. In our CHIME maps, we expect to see excesses of emission whenever there's neutral hydrogen. So if we do a cross correlation, we expect there to be an anti-correlation between the level of the quasar spectrum and the CHIME maps. And if we perform the same kind of procedure that we did, where we look in the CHIME maps at the location of all of these dips and try and do some averaging over all of those locations in the CHIME maps, we measure this cross correlation with the correct sign, the anti-correlation, at about 9 sigma at an effective redshift of 2.3, which is significantly higher than the previous record we already set for the highest redshift measurement of 21 centimeter emission. This analysis was mostly led by a graduate student at UBC, Tristan Pinsonneau-Marotte, who should be arriving at KIPAC any week now, I believe, as a new postdoc fellow. So there's a further connection which will build this legacy of KIPAC and build on the expertise here in line intensity mapping. Very quickly, I have many sub-bullets here. I won't go through each one, but just the near term for CHIME itself, the near-term outlook is more cross correlations. There's more of these kind of combinations with other data sets, which I believe are possible with existing data. And at ASU, I'm starting to build up a group which will pursue some of these analyses, including the data itself, as well as the theory and simulations needed to interpret them. We're also working internally on systematics control and building towards our first measurement of the auto power spectrum, which is really the goal here, to try and measure the 21 centimeter fluctuations in the maps themselves without relying on other data. The future of CHIME, we're currently applying for funding to keep it operating through 2029, and this is partially secured. But beyond this, there's a sibling experiment called CORD, which is currently being constructed right next door. This has a slightly different design, but it's designed to have better systematics control, higher sensitivity, and survey much more cosmic volume than CHIME, up to redshift 3.7. And so this will continue this theme of bootstrapping our way towards getting real interesting cosmological constraints from 21 centimeter intensity mapping. And so that's everything I wanted to say. The take-home message I would like to communicate is that line intensity mapping is a new promising complement to traditional galaxy surveys, and the field is evolving very rapidly. There are new experiments being developed and coming online all the time. And there are new first detections or first constraints happening all the time, some of whom are also very interesting, but I didn't have time to talk about in detail. And KIPAC has made a lot of key contributions here, both in terms of science and in terms of training people to go out into the world and find their own problems that they can try and solve. So I think I personally benefited a lot from this kind of training, and it makes me happy to return and share some of these results with you today. So thanks very much.
Thanks a lot, Simon. Questions for Simon? Yep, Dan and then Chiwei.
Hey, so I was interested in that result you showed with the line offset in the QSOs. I wonder if you could just say a little bit more about how much of that is due to an offset of the H1 line versus the lines that are used to calculate the redshift of those galaxies, and what would need to be done to disentangle those to actually learn about the gas dynamics in the QSOs.
Yeah, so I think we did various validation checks on the data to try and determine whether there are any systematic shifts in the H1 itself. And we didn't, in those attempts to disentangle, we didn't find any evidence for the shifts in the H1. So we attributed all to the quasars. Another important point I should mention is that CHIME's redshift sensitivity, it's such that we're not only measuring 21 centimeter emission associated with the objects themselves, we're also measuring emission from nearby objects whose positions are correlated with the catalog objects by large scale structure. And so there's a bit of ambiguity in really disentangling that carefully. There's some degeneracy between the objects themselves and the nearby correlated objects. But with a sufficiently good model, you can attempt to tease this out and break this degeneracy. But it's kind of a work in progress for us.
Thanks.
Yeah.
And Chiwei?
So two quick questions. So first one is, so you showed a cross correlation. So do you have a prediction of, in principle, when a autocorrelation, just from the signal noise, regardless of statistics, when it can be obtained? The second question is for your new experiment, the design is very different. So what have you learned from CHIME that you kind of ported into the second design?
Yeah, thanks. So for the first question, I don't want to give you a detailed timeline for the auto spectrum. I will say that for the statistical sensitivity, we're already there. If there were no systematics, we could have a booming detection of the auto spectrum. What we find when we add more data is that the noise integrates down as you would expect in the experiment, but we're still running into very low level systematics, which only appear after a lot of filtering. And so there's a lot of iteration in just trying to discover new systematics, identify and remove them. I would predict that an auto spectrum detection with CHIME is conceivable in the not too distant future. That's what I would say. And then for the second question, you asked about the chord experiment. And so the main design difference between chord and CHIME is clearly that we're working with individual differences instead of these CHIME cylinders. The CHIME cylinders are a good idea because they enable you to see a lot of the sky a lot of the time, and they also make calibration a bit easier, but they also introduce several problems, namely the shape of the beam response to the sky from an individual cylinder is incredibly complicated. You can have standing waves within the cylinder, which cause all sorts of ripples in the beam. And also having the CHIME antennas so close to another means that they just broadcast noise from the electronics, which is then measured by nearby antennas. And this is also a problem that we have to deal with. The core dishes are designed to try and circumvent both of these problems. And so the hope is that with these plus some other careful specifications of the dishes that we can overcome some of these beam measurement and crosstalk issues in CHIME.
So that was a very nice talk, Simon. And I really love the work that you've done doing the cross correlation with the galaxies to get at these systematics. And I'm just wondering, because I think it really shows how these surveys work together to be better. You are identifying ways that the quasar redshifts can be improved, and that maybe will allow us to understand more about quasar outflows, et cetera. The quasars are letting you get to this signal. What about Milky Way foregrounds? Because there are these huge data sets now in the Milky Way and local volume in the optical that may be able to help with some of the other issues, because with these new facilities and with CHIME even, you know, it's a hard measurement with lots of gnarly foregrounds. Should we be thinking in the optical and infrared community about how to either do targeting that kind of helps with those issues, or data serving that helps you analyze that data to get at those other systematics?
I think this could help to a certain extent. As you probably know, our external knowledge of these Milky Way foregrounds, our best data set is from 1982, I think, the Haslam 408 megahertz map. And that's really the best template that we have for these foregrounds. So more external knowledge of the physical nature of the foregrounds would be helpful. However, the main challenge we have in CHIME is that these foregrounds, which should be pretty smooth spectrum, get convolved into all sorts of nasty masking and instrumental issues in CHIME. And our main challenge is actually understanding those issues and being able to deconvolve them. So we could talk more about precise observables that are possible in other wavelengths, but I would expect the main bottleneck will be actually just careful design and characterization of the telescope itself.
Great, thanks a lot. In the interest of time, we'll stop there, and feel free to ask more questions.